So let's throw in the effect of temperature. Most chemical reactions are very sensitive to temperature. Their rates change quite dramatically with temperature. As an example, a 10 degrees Celsius increase in temperature can double or triple the rate of a typical biological reaction. And that's why your body controls your temperature so carefully, because if you get too warm or too cold, then the reactions don't work like they're supposed to and you die, right? So the rate constant, K, is only a constant when the temperature remains a constant. The rate will be different at a different temperature, and so the rate constant will be different at a different temperature. So the temperature dependence of the reaction rate is found within the rate constant. And we generally see that rate constants increase with temperature. As the temperature gets warmer, the rate constant gets larger. Rate constants generally increase with temperature. Larger temperature, larger rate constant. So the Arrhenius Equation gives us the relationship between the rate constant and the temperature. So this is the Arrhenius Equation. K is equal to A, that's the frequency factor, times E raised to the power, and this whole thing is the exponent. It's -1 times the activation energy divided by R, the gas constant, and T, the temperature in kelvins. And we want to use this 8.314 joules per mole Kelvin gas constant so that the units are going to work out. So EA is the activation energy, and this whole term here is called the exponential factor. So we have the frequency factor and the exponential factor. So we need to talk about activation energy and frequency factor. So even if a reaction is energetically favorable, it's an exothermic reaction, the products are lower in energy, there's still a certain amount of energy that's needed to make the reaction happen. And that's called the activation energy. Activation energy, abbreviated capital E with a subscript A. This is the energy barrier that needs to be overcome. And that can include a lot of different factors. But when we draw an energy diagram, we can draw one like this. So energy on the y-axis, reaction progress on the x-axis. And if we start with our reactants at some energy, as the reaction occurs, we need to go up in energy. We need enough energy to get up and over this hump. And then the reaction occurs and we make the products. The products here are lower in energy than the reactants. And this distance here is the activation energy. So if the reaction doesn't have enough activation energy, this is a little bit like putt-putt golf, miniature golf. You know, they have all those little humps on the greens. And you have to hit the ball hard enough that it's going to have enough energy to go up and over the hump. Otherwise, it just rolls back at you, right? So if there's not enough energy, it doesn't go over the hump, no reaction happens. The frequency factor is the number of times that the barrier is approached per unit time. So how many times do you hit the ball towards the hump? That's the frequency factor. And so both of these play a part in the rate constant. Any questions yet?
So the frequency factor would be how many times the ball's hit and what would the activation energy?
The activation energy is how high the hump is. Mm-hmm. Yep. Anybody else?
Well, this kind of applies to our worksheet when we're talking about the differences between kind of a regular, right, endothermic, exothermic versus one of these that has the activation energy.
Well, the diagrams that it was asking you to do in worksheet 0 didn't have activation energies in them.
But you said.
But it's like them.
It says examine the figures on page, which is those, and compare the diagrams to the diagrams that we drew.
Okay.
And so.
Oh, yeah.
The difference is.
So the difference is that this shows the activation energy.
Yeah, but the similarities
Right, so this is an exothermic reaction, starts at high energy, goes to low energy. But here we're showing this activation energy. All reactions have some activation energy, but some of them are very, very small, and so you wouldn't even notice. But there has to be some energy there. That's right, they can't do that. So if we think about this, because what does approach the barrier mean? Well, do you have a question?
Yeah, quick question. Is the activation energy and the frequency factor, are they like I don't want to say inversely, but the opposite, but inversely. Like if the activation energy is higher, will the frequency factor
No,
be-
they are
or
independent.
Are they okay?
So they come from the Arrhenius equation here, and so A is the frequency factor, and the activation energy is that EA, and they are not related to each other. So, if we talk about miniature golf, we can think of a frequency factor as how many times per minute are you hitting the ball towards that little hump. But what does it mean for a chemical reaction to approach that barrier? We can think of this reaction where we've got CH3NC, which is methyl isonitrile, and it undergoes a rearrangement to form acetonitrile, CH3CN. So this is a really weird reaction. So what happens here is the nitrogen and the carbon change places in the reaction. This is weird. This is not something we looked at in Chem 1A. So we've got this molecule, and it undergoes a reaction. It rearranges itself to form this. So the molecule goes through a high energy state in which the carbon and the nitrogen are in the process of twisting, right? They're in the process of changing places. So we have to weaken the carbon-nitrogen bond in order to allow this NC group to begin to rotate. So this is the activated complex, where instead of the carbon being bonded to nitrogen like it was in the reactant, or to the carbon as it is in the product, it's kind of bonded to sort of both of them and none of them. It's like in the middle. This is a transition state. It doesn't hang around for a long time, but that's what you have to go through to get to the product. Here we have this hump is the activation energy needed to achieve that activated state or the transition state. The higher the activation energy, the slower the rate of reaction. The harder it is to get up and over that hill. So the frequency factor represents the number of approaches to the activation barrier per unit time. So as that NC group approaches the activation barrier, each time it begins to rotate. So it begins to rotate, and sometimes it continues to rotate and it finishes, and other times it starts rotating and it doesn't quite make it and comes back. It's like that ball going up and oh, we didn't make it, coming back down. Right? Sometimes you go up and just barely over and then it goes down. So we think of this group as wagging, vibrating side to side. So this group is wagging back and forth, you could almost like a dog wagging its tail. And if it comes far enough over, it has enough energy to get far enough over, it can reach that transition state and then continue around, and we get that rearrangement and the bond forms with the carbon instead of the nitrogen. So every time it begins to rotate is an approach to the activation barrier. And how many times that occurs, say per minute or per second, is the frequency factor. Any questions?
So is it the addition of energy is making the one group on the molecule rotate more or less?
There's energy involved in making that tail wag. Just like when a dog wags its tail, it requires energy to move it, right? It has to have enough energy to get to that critical point of going over.
Why is it that it only affects the one half of the molecule?
Well, in this particular reaction, that's the only thing that's changing.
Okay.
I suppose you could think of this being stationary and that wagging. That would be the tail wagging the dog.
Oh.
But, it's neither here nor there. It's a matter of perspective.
So it's just targeting the central carbon-nitrogen bond because it happens to be the weakest versus the triple bond on the C.
Yeah, this triple bond is very strong, and it's not actually going to break. This is going to get weakened as it gets pulled and out of place, and then when you get it far enough, that's weak enough that it'll say, ooh, there's the nitrogen, make a bond with the nitrogen. So we don't want to think too intensely about this specific reaction. We're just using it as an example. I'm trying to think of something else in life where stuff comes up and almost goes over, but not quite. A roller coaster that gets stuck? Or maybe like a gymnast on the parallel bars. Uneven bars, that's what they are. And she's trying to swing all the way around, right? And so she swings, and the first time she doesn't get up high enough, and so she comes back, and then she gets more momentum, and then finally she gets all the way up to the top, and she may come back, or she may go all the way around. And so that's kind of what this is. It's how many approaches per second. The more approaches per second, or whatever unit of time you have, the more likely you are to have the reaction occur, and the faster the rate would be. And then the smaller the activation energy, that means that more of those approaches are going to be successful, and so your rate will be higher. So the exponential factor is the fraction of molecules that have enough energy to make it over the activation barrier on a given approach. So that ends up being a number between 0 and 1. It's the fraction of approaches that are successful. So if you approached 100 times and 75 times you got over, that would be 75 out of 100, or 0.75, right? So that would be the exponential factor, the fraction of molecules that make it over the activation barrier. Oh, I could have used this example that's written here right on the slide instead of making one up. So if your frequency factor is 10 to the 9th per second, and the exponential factor is 10 to the minus 7, that's 1 over 10 to the 7, that's your exponential factor. So this fraction of approaches are going to be successful. So we multiply the frequency factor times the exponential factor, and that gives us the rate constant. So here it would be 100 per second. So that exponential factor, the fraction of approaches that are successful, depends on the temperature and on the activation energy. So at a higher activation energy, the hill is higher, it's harder to get over, and so your exponential factor will be smaller. If the temperature is higher, then we have more kinetic energy, and so we're more likely to be successful. So if we have low activation energy and high temperature, this factor is going to approach 1, where every approach is successful. If we have a high activation energy and a low temperature, then it's going to approach 0. So here, this would be a high activation energy. And this would be a low activation energy. It's that little tiny bit there. So at low temperature, molecules are moving slowly. They have less kinetic energy. So if we have a high barrier and pokey molecules, slow molecules, we're going to approach a factor of 0 here, where nobody makes it over. Just not going to happen. Here, if we have a low activation energy, the barrier is really low, and we have a high temperature, very energetic molecules. That tail is just wagging furiously. We'll approach a factor of 1, where every approach results in a reaction. Does that make sense? So if we look at a bunch of molecules in a sample at a particular temperature, they do not all have the same amount of kinetic energy. The temperature is the average kinetic energy of the molecules. Some of them will be moving faster and some will be moving slower, higher and lower energies. We're just looking at the average. So here we've got fraction of molecules having a particular energy as a function of energy. Here we have temperature 1 and temperature 2. What happens when you increase the temperature from temperature 1 to temperature 2 is the curve spreads out. And so the fraction of molecules with the higher kinetic energy becomes larger. So the area under here's the activation energy. That's how much energy it has to have to get over the hump. For the blue, the area under the curve here represents the molecules that are going to make it. And here, the area under the curve, that's the physics people doing fun, explosive things. Nothing to worry about. This area represents the molecules that will be successful, that will have enough kinetic energy. Any questions about that?
So in this diagram, T2 is a higher temperature than
Yes.
T1?
So T2 is greater than T1. If I drew a lower, maybe you call it T0, it might be something like that. So it would get narrower. As the temperature gets lower, the distribution becomes more narrow. And this, I might not really have any that have enough energy to get over now. So summary of that. Frequency factor, how many times per unit time the reactants approach the barrier. The exponential factor is the fraction of approaches that are successful. The exponential factor increases with temperature and decreases as the activation energy becomes larger. So let's see if that made any sense. Which statement best explains why reaction rates generally increase with increasing temperature? So choice A, reaction rates increase with increasing temperature because as temperature increases, a greater fraction of molecules have enough thermal energy to surmount the activation barrier. Well, what do you think about that statement? That sounds good, right? It's always a little scary when the first one sounds good. It's like, yeah, that greater fraction of the molecules have enough thermal energy. It's kind of what we were talking about with this diagram, right? Higher temperature, we've got more molecules that have enough energy. So we liken that one. How about B? Reaction rates increase with increasing temperature because as temperature increases, the pre-exponential factor of the rate constant increases. That would be the A, the frequency factor. Did we talk about the frequency factor depending on temperature? No, we didn't talk about that at all. So probably not that one. Reaction rates increase with increasing temperature because as temperature increases, molecules decompose into their constituent atoms, which can then form new bonds to form the products. That's just like not even close to what we were talking about, right? I mean, it sounds good. The words all sound good, like it's like very scientific, right? But it has nothing to do with what we were talking about. So A is the correct answer. questions? So how do we figure out what those factors are? We can figure out what the frequency factor and the activation energy are by measuring the rate constant at different temperatures. So the rate constant changes when the temperature changes. So we can set up the reaction and observe it at different temperatures, and then we can make a graph. So this is the Arrhenius equation. If we take the natural logarithm of both sides and do a little bit of rearranging, we get this. So this is the linear form of the Arrhenius equation. So this is our y, and x is 1 over temperature, b is the natural log of a, and the slope is negative activation energy over r. So we can graph this data, and from the slope and the intercept, we can calculate these two factors, the frequency factor and the activation energy. So the frequency factor does depend on temperature, but not very much. Like it says down here, the temperature dependence of A is relatively small and is often ignored. We are going to ignore it because we can. Okay. So here is an example of using an Arrhenius plot. The decomposition of ozone shown here is important to many atmospheric reactions. The study of the kinetics of the reaction results in the data shown below. Determine the value of the frequency factor and activation energy for the reaction. So let's look at what we've got here. We've got temperature 600 to 1200 Kelvin. We've got rate constants for those temperatures. And here we've got another column of temperatures. The temperature just went up and up and up, and here's the rate constants for those. So what we want to do is we want to graph the natural log of the rate constant on the y-axis and 1 over the temperature on the x-axis. So through the magic of PowerPoint, there's the graph. And it's a nice straight line, and the computer can tell us what the linear regression line is. So here the line is y equals negative 1.12 x, 1.12 times 10 to the 4th x plus 26.8. And that matches up with our linear form of the Arrhenius equation. So the natural log of A is equal to 26.8. That's the intercept. The natural log of A is equal to the intercept, 26.8. And so if we want to know what A is e to the 26.8. Which is huge, 4.36 times 10 to the 11th. That's a big, big number. And then here we have the slope of the line. And the slope here is negative EA over R. So negative EA over R is equal to negative 1.12 times 10 to the 4th. Well, we know what R is. Negative EA over 8.314 is equal to negative 1.12 times 10 to the 4th. So we solve for EA. We multiply both sides by -1. We multiply by 8.314. We end up with EA is equal to 8.314 times 1.12 times 10 to the 4th. That's what my calculator tells me. What are the units of the activation energy? The activation energy. They might be energy units. Joules. Because the unit on this guy here is joules per mole Kelvin. What's the unit on the frequency factor? A.
They still do the same thing. They're not considered a concentration at this point, right?
A is not the concentration. We were using A in brackets as concentration, but this is the frequency factor. Well, what was the definition of frequency factor? It's how many times the molecule wags, or how many times it approaches the barrier per second, per time. And the standard unit for time in the metric system is seconds, and so this would have units of seconds to the -1, or per second. Any questions?
Will that always be in flat seconds, or will it be the femtoseconds?
These should always end up in seconds. Yeah. Now, if we wanted to use this number reported or something and we didn't like how big it was, then we could change the seconds. But in the equations, they tend to go with base units. Yeah.
Now, why is it s to the -1 instead of just a second?
It's per second. It's how many approaches per second. So it's like a frequency. It's a frequency factor. Well, that's a good question. That's a good question. And, you know, this number is kind of ugly, right? So we might want to express that a little better. We could say, well, you know, maybe 3 sig figs, 9.31 times 10 to the 4th joules. Or we could get into kilojoules and say 93.1 kilojoules. Those are all the same thing. Yeah.
Is there any instance where like temperature's increasing, so you would have the frequency factor be like per second squared?
We are going to completely ignore the temperature dependence of the frequency factor. It's usually pretty small, and so it's beyond the scope of this class. If you really get into kinetics, then you do have to consider things like that. Yeah, so the units on the activation energy are actually joules per mole. Okay, for the decomposition of ozone in that example, use the results to predict the rate constant at 298 Kelvin. Well, I'm going to go back and write these down because I can't remember them. 4.36 times 10 to the 11, 93.1 kilojoules per mole. Use the results to predict the rate constant at 298 Kelvin. Well, how is the rate constant K related to these things? We had an equation, the Arrhenius equation. So the Arrhenius equation is K is equal to the frequency factor times E raised to the negative EA divided by RT. So to find the rate constant, we need the frequency factor, the activation energy, and the temperature. And of course, we always know the gas constant. So from the previous problem, we've got 4.36 times 10 to the 11th as our frequency factor. And e to the negative, I'm sorry, I didn't want to do that. EA is our activation energy, 93.1 kilojoules per mole. And R is 8.314 joules per mole Kelvin. And the temperature was given to us as 298 Kelvin. So, is there any unit problems that we might encounter here? Yeah, I've got the activation energy expressed in kilojoules, and this gas constant is in joules. And so I want to use the activation energy in terms of joules. So now I'm just going to plug everything in. So I got 4.36 times 10 to the 11th E raised to the mass of 9.31 times 10 to the 4th divided by, that's an 8.314 times 298. It's one thing to get that written down. It's another thing to communicate correctly with your calculator and get the right answer. And unfortunately, we need to do both. So on the TI-36X Pro, I'm going to type in that frequency factor 4.36 EE11 times, and then e to the power of negative 9.31 EE4 divided by 8.314 divided by 298. Close the parentheses and press equals. And I'm getting, let's see, 1, 2, 5. 2.0891 times 10 to the minus 5. Three significant figures is probably pretty safe, so 2.09 times 10 to the minus 5. Any questions? Did anybody else get their calculator to show them that answer? Okay. Good. Question?
For the last one, it just said solution, so how do we go to solve for the activation energy and the frequency factor for the previous one?
For the previous one?
Yeah, well, it's a solution line. How do we know that's a result?
Well, it said determine the frequency factor and activation energy. Yeah. Because that wasn't on this slide, which is where we did all the work. This is the same. Yeah, this is the solution. Sorry. This is the problem, and this is example 15.7. This is the solution.
This won't have a unit. Well, everything.
Yeah, so when I was talking about the frequency factor and per seconds, I realize now that that was wrong. Because it's a factor, it's a fraction out of, how many times out of are you successful. So it doesn't have a unit.
Yeah, because if it's a number
Yeah.
of times, you can't have
Well, yeah, it's,
technically you can't have.
if we go back to this, This is one of those places where the units kind of go away. Oh, look, I wrote the things on there and I forgot to press the button. Yeah, so 2.07, I came up with 2.09. That's close enough that we don't need to worry about it. It's not always practical to get a whole bunch of data like that. Some chemical reactions will not actually work over a wide range of temperatures because the compounds decompose or whatever, or it's very difficult to measure. So we can make this into a 2-point form where if you have the rate constant at 2 different temperatures, you can calculate the activation energy. This is a little different than what your book shows you. So your book is going to show you this, I believe. And the difference here is this one has a negative sign out here, and this one doesn't, and so these got rearranged. The reason I like this one is that because we have K is equal to A E to the negative EA over RT. And we did the linear form. We got the natural log of K was equal to negative EA over R times 1 over T plus natural log of A. And this is K2 over K1, and it's 1 over T2 minus 1 over T1. It's following that pattern of final minus initial. Yes?
So do you want us to write the bottom or the top of it?
This is the one I'm giving you on the cheat sheet for the exam, the equation sheet. And that's the one I'm going to be using in class.
Okay.
I'm just telling you about this because if you look in the book and you see this one,
Yeah, it's the same thing.
it is the same thing. This one just intuitively makes more sense to me.
It's easier, okay.
Yeah, because it goes with all the others. The good news is you don't have to memorize either one of them because I'm going to give them to you on the exam. So consider the reaction between nitrogen dioxide and carbon monoxide. The rate constant at 701 Kelvin is measured as 2.57 per molarity per inverse molarity per second, and 895 K, it's 567. Find the activation energy in kilojoules per mole. So we have 2 temperatures and 2 rate constants. We're going to use the 2-point form of the equation. So the natural log of K2 over K1 equals negative activation energy over R, 1 over T2 minus 1 over T1. So we need to identify what's T1 and what's T2. It doesn't matter which one we pick. Let's just make the first one the first one. So we're going to say that T1 is equal to 701 Kelvin, and it says that the rate constant there is 2.57. And the other temperature we'll call temperature 2, 895 Kelvin. And at that temperature, the rate constant is 567. So I'm going to take those numbers and put them into the equation. So I've got the natural log of K2, 567, divided by K1 I hope this is going to fit, minus EA over R is 8.314 joules per mole Kelvin. And then our temperatures, 1 over T2, 895, minus 1 over T1, 701. Now, you can rearrange this equation and plug the numbers in, but that gets really ugly. And so I encourage you to learn how to do this largely on your calculator. So on my calculator, what I'm going to do is I'm first going to calculate what's on the left side. So the natural logarithm of 567 divided by 2.57 equals. I'm going to write this down just so you can see it. And then over here, I could figure out what this is, right? And what I'd like to do is I'd like to take this side and divide by this mess to move it over. So I'm going to divide by, open parentheses, 1 divided by 895 minus 1 divided by 701, close the parentheses, and press equals. Now I've got negative 17564.2 is equal to negative EA over R. You wouldn't necessarily write all this down. I'm just trying to help you see the steps I'm doing. So that's not what I wanted. This is what I wanted. I took this number and I divided by this, and that's how I got this. So this is equal to negative EA over 8.314. So I've got that number in my calculator. I'm going to multiply by 8.314.
Wait, at this step on the left-hand side, what are your units? Negative 17,000.
So I think they're mole kelvins. No, I think they're kelvins.
Like that.
Yeah, so EA is joules per mole.
Because
And
the natural
this is
log up there, they cancel out the
joules
molarity
per mole
second.
Kelvin. Yes. Here the per mole, the m to the minus 1, s to the minus 1, those canceled out.
Okay.
Those canceled out. And here I had kelvins, and so then I was getting rid of the kelvins. Actually, let's just agree not to talk about that. Would that be okay? I understand the question. I don't think the answer is going to be very helpful. So I still have this number in my calculator. I multiply by 8.314. I get negative 146,028.8, and that's equal to negative EA. And then getting rid of the negative signs is easy enough. Multiply both sides by negative 1. So EA is equal to, we want this in kilojoules per mole. The standard units here, which came from R, were joules. And so this is coming out in joules. And so if I divide by 1,000, I'm going to get 146 kilojoules per mole. So in Chem 1A, it's not actually yelling, but I'm just like repeating myself all the time. Always write all the units. Make sure all the units cancel out. And some of you were like, yeah, but it'll be fine, and it was fine, and you were like, why did I have to do that? Well, this is a situation where, yeah, you kind of just start with the right units, and the units will come out right in the end, and you don't get too upset about it. The thing you have to watch out for, though, is the units on this, 8.314, are joules per mole Kelvin. So temperatures have to be in Kelvin for several other reasons as well, and the energy comes out in joules. So if you're starting with something in kilojoules, you have to convert to joules. If you need kilojoules, you have to convert, okay? So we see if I got the right answer. Huh? That's 150. 146 rounds to, yeah.
In that case, like with this, would you prefer to like round off after like 4 significant digits, or would you want us to put like the whole number in? Because I had got a different number because I put the number in there. I just put the answer over.
Right. So what I was doing is I wasn't actually these were a little bit rounded. I wasn't rounding them at all. I was just going them in my calculator.
Okay.
I didn't round them at all in my calculator. And so ideally you'd be able to go from this written out equation straight to this down here without writing anything down. Yeah. Every time you write something down, you can make a mistake. Every time you put it back in your calculator, you can make a mistake. And then there's always the rounding issue. Yes?
How did you know she was 8.314? Because there's no volume?
Well,
Any of the other Greek constants?
so we use 0.08206 liter atmospheres per mole Kelvin when we've got volumes and pressures. And here we're not talking about volumes and pressures, but we are talking about energy. Yeah.
It's something you just get used to and know this goes in there.
Yeah. If you very carefully followed all the units, then you'd realize, oh, wait, I need to convert. And it can be done, but we don't want to do that.
Okay.
Yeah. If we go back, oh, I went too far. Where did I? Oh, here it is. It says the gas constant is 8.314 joules per mole Kelvin. Vanessa.
Okay.
That's what tells us what R is.
Yeah, but that was so.
I know, it was so many slides ago. How am I supposed to remember that?
Total loss.
Okay. You use the results from example 15.8 and the given rate constant of the reaction at either of the two temperatures to predict the rate constant for this reaction at 525 Kelvin. No, I didn't do anything so useful. We need that answer. I'm going to go ahead and use the 146. So in that previous problem, we calculated our activation energy. So that was 146 kilojoules per mole. Now we want to know what the rate constant will be at 525 Kelvin. So since this is titled Using the Two-Point Arrhenius Equation, that's the approach they intend for us to take. It's not the only way it can be done, but we'll go with it. So, we're supposed to use the given rate constant of the reaction at either of the two temperatures from the previous example to predict the rate constant at this new temperature. Now, when I'm solving for one of these rate constants, it's easiest if I'm solving for the one on the top. Just because it's in the numerator, everything's easier in the numerator. So I want this 575 to be the second temperature. I'm solving for K2 then, so I need a T1 and a K1. Could somebody tell me what those are from the previous example? You can pick either of them. I think one was 701 Kelvin. So what was the rate constant at 701? 2.57, thank you. So the natural log of K2 divided by K1, 2.57 is equal to negative 146 kilojoules per mole. I need that to be joules per mole. Down here I have R, 8.314 joules per mole Kelvin. The joules and the moles cancel out. T2 is 525 Kelvin, and T1 is 701 Kelvin. When I subtract these, I end up with 1 over Kelvin, and this is 1 over Kelvin, and so the Kelvins cancel out too. And this ends up being unitless on that side. So I can calculate what this right side is. Negative 146,000 divided by 8.314 times the quantity 1 over 525 minus 1 over 701. So I've got the natural log of K2 over K1 is equal to that. How do I undo natural logarithm? Anti-log, e to the x. So I do e to the x of both sides. That cancels the natural logarithm on this side and gives me e to the minus 8.398 on that side. And then if I multiply by 2.57, on both sides, that cancels out, and now I can figure out what K2 is. So e raised to the negative 8.398, close the parentheses, times 2.57. The units on K2 would have to be the same as the units on K1. And they're probably going to round that to 5.8 would be my guess. 6.8 times 10 to the minus 4. Not even close. What'd I do wrong? 6.13. Okay. So I'm going to check my math. Did anybody else get 6.13 times 10 to the minus 4?
Would
Ooh.
it matter, would it matter whichever first rate constant?
If we use, no, that shouldn't matter. Which of those temperatures we used? I'm thinking I used the unrounded, less rounded. I'm thinking if I use 1.5 in there, that might make the difference. Because 5.8 and 6.1 are not that far apart. You know, usually when you screw up, it's like super different. This time I got 4.6 times 10 to the minus 4. What?
Do you think you could have just used like a different T2?
Well, I checked that we used the match. So 701 and 2.57 go together. If somebody wants to try it with the 895 and the 567, it should give us the same result. Just trying to think of what I might have done wrong.
Maybe the slide answer's wrong.
It's possible. Okay, so we've gone back and looked at it, and we can't seem to find out what's wrong. It's pretty close, and I think we're all really tired of this problem, so we're going to move on. Then they just keep doing it, and then we don't have to learn anything new. I know how that works. Here's one without calculations. Reaction A and reaction B have identical frequency factors. However, reaction B has a higher activation energy than reaction A. Which reaction has a greater rate constant at room temperature? So reaction A and reaction B have identical frequency factors, but their activation energies are different. So if you think of, here is your person playing miniature golf. Oh, you got to have your hands down, and there's your club, and here's your little yellow golf ball. Right? So frequency factor is how many times do you hit it at the barrier per second? Right? So we got two people, and they're doing it at the same rate. There's the ball. Here's our other little person. Here's golf club. They're hitting them at the same rate. The temperature is also the same. The temperature is how much energy the ball has. So which one is going to get balls over faster? A. Because you don't have to have as much energy to get over. And so a bigger range of, because those balls, on average, you're going to have the same kinetic energy, but some of them are going to be higher and some are going to be lower. And here, most of them are going to get over. So the greater rate constant, the faster rate would be A. So there are different levels of understanding this. There's like really, really understanding it, and there's just remembering enough to answer questions like this. I mean, we can't do everything. So some of these questions, if you just kind of have a general knowledge of what's going on here, you can guess the correct answer. So small activation energy, large activation energy. Everything else the same. This is going to be easier, it's going to be faster. Now, if they were talking about frequency factors and temperatures being different, then things get a lot more complicated. But we didn't ask you about that. What's next? Ooh, collision model. We get a video here. So, looking at the frequency factor for a reaction involving two gas phase reactants. The one we looked at before was a single molecule wagging its tail, right? Now we're going to look at a more common situation where we have two molecules in the gas state and they have to get together somehow to react. So the chemical reaction will occur if the things collide and they collide with enough energy, right? So each approach to the activation barrier now is a collision between the reaction molecules. The frequency factor here is usually less than the number of collisions per second. Any ideas why? Do all the collisions go over? Do all the collisions have enough energy? No, they don't. So let's watch this.
Like you could have like 30 collisions, but only like 3 go over.
Right. Only 3 of them might have enough energy.
Climate change and other factors are straining California's water systems. So,
have you ever been to a demolition derby? Basically, a bunch of people driving cars around a field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course...
Oh, awesome. Hang on to that thought, please. Don't want to miss...
Have you ever been to a demolition derby? Basically, a bunch of people driving cars around a field doing their best to ram into each other while protecting themselves as much as possible. The goal, of course, is to damage the other car so badly that they can't be driven anymore. The driver of the last operational car wins. You know Crash Course Chemistry well enough to know that I probably wouldn't have mentioned this if it didn't have some relation to chemistry, so yeah, it does. Chemical reactions basically work just like this. Atoms and molecules move around their environment, occasionally ramming into each other. If they do it just right, a reaction happens between them, and if enough of them do it, the concentration of the reacting molecules will go down, while the concentration of the products goes up. It's weird. But it's not as simple as it sounds. For demolition drivers or for chemicals, in both cases, a lot of the collisions that occur have very little effect on the end result. One molecule hitting another doesn't mean a reaction is going to take place, in the same way that just randomly bumping into another guy's car doesn't mean that you're going to ram him out of the derby. So what makes a collision effective? The hit has to be hard enough, and it has to be aligned just right. The branch of chemistry that studies how these collisions affect the rate of reactions is kinetics. And if you ask me, it's just as exciting and a heck of a lot more useful than demolition derbies. If only they sold funnel cakes in chemistry class. So, if chemical reactions only work when particles bang into each other good and hard, just how hard do they have to bang into each other? Every reaction has a minimum amount of energy required to get it started. This is known as the activation energy. Molecules require this much energy to hit other molecules hard enough to break them apart and reform them in different ways. Without it, nothing will happen. It's like a hill that molecules have to get over before they can go any further. So where do they get this energy? Well, it's kinetic energy, the actual speed of the particles. So just like the cars at a demolition derby, all else being equal, the faster the particles move, the harder the collision will be. But still, no matter how hard they hit, it won't do any good if they're not hitting the right way, in the right places. Like if you keep smashing into the back of a guy's trunk, that's not going to stop his car. There's no engine back there. You can bang Velcro together all day and night, and if it's not turned the right way, it'll never stick together. Same thing with molecules. As an example, take nitric oxide, one of the byproducts of gasoline combustion, and something that you can smell quite clearly at a demolition derby. Under the right conditions, it reacts with hydrogen gas to produce nitrogen gas and water. But the molecules have to hit each other just the right way. To make N2, two NOs have to collide in such a way that the nitrogens are together, and to get H2O, a molecule of H2 has to collide with the oxygen side of an NO molecule. Just like Velcro being turned the wrong way, you can smack the inside against the H2 all day and you'll never get any water from it. And let's say that we're having a lot of solid, effective collisions between the molecules. The reaction should hum along with no further hindrances, right? Well, yes and no. Once the energy requirements are met, the reaction will proceed, but its speed, or reaction rate, will vary wildly from super fast to super slow. So the reaction rate, that's the rate at which the concentrations of the reactants decrease, and this has to be determined experimentally. It can't be calculated from the energy change or any other thermodynamic factor. One useful way to think about the rate is a quantity called the reactions rate law. It describes the relationship between the initial concentrations of the reactants and the rate at which they react. The rate law for a reaction is written like this. The rate equals a constant K times the concentrations of each reactant raised to some power. Notice that only the reactants are used for this, not the products. The rate law for our nitric oxide reaction then ends up as K times the nitric oxide concentration raised to some power times the hydrogen concentration also raised to some power. So you're probably wondering about all those raised to some power, like what power? And you should be wondering that. The exponents in rate laws are tricky, even for professional chemists and engineers, because like I said, they can only be determined experimentally. It's kind of intense, but we can handle it. Check it out. Suppose we did the reaction a few different ways and calculated the rate for each instance. Let's say that with the first reaction, we got a rate of 0.0060 moles per liter per second. Then we repeat the reaction with the same amount of nitric oxide, but this time with twice as much hydrogen as before. And now we find that the rate of the reaction is 0.012 moles per liter per second. What does this tell us? Well, doubling the hydrogen doubled the rate, meaning that the rate and the H2 concentration change in exactly the same way. So in the rate law, this can be expressed by the concentration being raised to the power of 1. Finally, we do it one last time with the original amount of hydrogen, but twice as much NO. And this time, we find that we get a rate of 0.048 moles per liter per second. Doubling the nitric oxide caused the rate to increase by 8 times, and that can be expressed in mathematical terms by cubing the concentration term. This means that the final rate law for this reaction reaction is K times the concentration of hydrogen gas to the first power, you don't need to write out the 1 obviously, times the concentration of nitric oxide cubed. A rate law in this form is said to be of the 4th order. We get that value by adding the exponents together, 3 plus 1. There is some math that isn't hard here. That equals 4. 4th order reactions are actually quite rare. Most reactions are of the 0, 1st, or 2nd order, but in all cases it's calculated exactly as we have done here. Now if you've watched our episode on equilibrium, this formula should look familiar to you. Equilibrium expressions also use bracketed concentrations with exponents, and that's no accident. Those formulas come from these ones. A reaction is at equilibrium when its forward and reverse rates are equal, right? So if we were to find the reverse rate law for a reaction, it would take the same form as the forward one, but using the initial concentrations for the products rather than the reactants. Think of like an imaginary reaction A plus B yields C plus D. The lowercase letters represent the coefficients of the reactants and products. The forward rate law is K times the initial concentration of A raised to some power times the initial concentration of B raised to some power, and the reverse is the same, but with C and D in place of A and B. Notice that these exponents are not, however, the coefficients of the balanced equation. If we write these two terms together to show that the forward and reverse rates are equal, like at equilibrium, and solve for a single constant, we get something that looks very much like an equilibrium expression. For mathematical reasons, the exponents don't translate, but yeah, basically this is where the equilibrium equations come from. Pretty cool. But if it's that simple, why don't all reactions just go to an equilibrium state and stay there? Well, sometimes the reverse reaction isn't thermodynamically spontaneous for one reason or another. Sometimes the forward reaction is so vigorous that any reactants that might reform are immediately pushed back into products. Or the products might physically separate and have little chance of colliding at all, like when products separate into solids and gases. Often though, it's just that the reverse reaction has such a high activation energy that the collisions are almost always ineffective. Because remember, most reactions don't happen instantly, boom, all at once. Instead, they happen in steps. And as with any multi-step process, the reaction can only happen as fast as the slowest step takes. And sometimes that step is very slow indeed. Since it's what controls how fast everything else can go, we call it the rate limiting or rate determining step. The slowest step is the one that has the highest activation energy. If the particles have trouble getting over that part of the energy hill, then they'll have trouble making it to the finish line no matter how fast the other steps are. So in the case of the nitric oxide reaction we've been discussing, there are actually 3 steps. First, the nitric oxide and the H2 form water and elemental nitrogen. Then, the nitrogen combines with another molecule of NO to form N2 and elemental oxygen. Finally, that atom of oxygen combines with another molecule of H2 to form water. Here, step 2 is the slow one, and no matter how fast you take the first step, the water product can never be produced until the nitrogen gas is. Problem is, we can't always afford to wait around for reactions to happen on their own. Sometimes they need to be forced along, and that's the job of catalysts. A catalyst is a chemical that lowers the activation energy of a reaction, thereby speeding it up without actually being changed by it. Catalysts take many different forms. They can be just another chemical added to the reaction vessel, a piece of metal that's in contact with the reacting chemicals, or even a gas that's added to the environment. One of the most common and important classes of catalysts are the enzymes in living things. Without them, many of the chemical processes that our bodies must do every day to keep us alive would slow essentially to a stop. We literally could not survive without them. So there you go. In demolition derbies and in chemistry, it all comes down to how hard you can hit and how well you can aim your punches. Chemistry, surprisingly exciting, even without fun breaks. Thanks for hanging out for this episode of Crash Course Chemistry. If you paid attention, you learned that chemical reactions depend on collisions between molecules and atoms, that the particles have to be oriented correctly when they collide, and that they have to collide with enough energy to meet the threshold for the reaction, known as the activation energy. You also learned how to write rate laws and figure out their exponents, and how to calculate the form or order of a rate law. You learned how rate laws are related to equilibrium expressions, and finally, you learned that chemical reactions actually happen in steps, that the slowest step determines the overall rate of the reaction, and that the reason for that comes right back around to the activation energy. This episode was written by Edie Gonzalez and edited by Blake DiPastino. Our chemistry consultant is Dr. Heiko Langner, and was filmed, edited, and directed by Nicholas Jenkins. The script supervisor was Michael Aranda, who is also our sound designer, and our graphics team is Thought Cafe.
Trying to find this It was just up there for a minute.
Important classes of catalysts are the enzymes in living things. Without them, many of the chemical processes.
It was a catalyst.
I think it was right after the catalyst slide.
Oh, a list of cattle.
Yeah, it was a list of cattle. I was like,
Around for reactions to happen on their own. Sometimes they need to be forced along, and that's the job of catalysts. A catalyst is a chemical that lowers the activation energy of a reaction, thereby speeding it up without actually being changed by it. Catalysts take
I love this guy's sense of humor. Yeah. I'm like, what? And then I got it. Okay. So we've got the collision model and mechanisms left. I think we can cover that next week, right? We have one more lecture day. So that was kind of a preview of some of the things we're going to be, we'll be talking about catalysts, not lists of catalysts, and we'll be talking about reaction mechanisms and how those affect the rate. Now somebody told me they solved our problem.
Yeah.
What did we do wrong?
This from this part. This I'm just kind of like, it's the limit. It's like, you can't go any further until this one finishes. The alcohol reacted like, you can't go further after this one because and that's very broad
The
sense.
limiting reactant is the thing that ruins the active product with you. The slowest step is the thing that makes the
6.1, that's good. That's good.
which is the slowest step.
I tend to the negative part.
Yeah.
See, I
I use a more negative there. I feel like it's probably like 7 p.m. And then that one said, is that too, if you did it to kilojoules, is it gonna be like 1.5 times 10 to the
Yeah, I think that was the
I
problem.
did it to the fit, not to the fourth. So if you twist it, and then you do the whole thing, then it probably will be.
Yeah, that was the problem.
It's the exponent.
Times 10 to the 10 to the third.
Yeah. Yeah, so that would be for kilojoules. I did it to the fifth joules per mole.
So that's where the problem was. It wasn't 146. It was 1,460. This is a little, you know.
It's fine. It's close enough.